my absolute pleasure to introduce today's colloquium speaker, Ivo Jimenez, who is a research scientist at UC Santa Cruz, an incubator fellow at UC Santa Cruz Center for Research on Open Source Software, and an adjunct professor at University of Sonora in Mexico. His particular interests are in large-scale distributed data management systems, applied aspects of data science, and reproducibility. And his recent PhD had focused on the practical aspect of reproducible evaluations of systems research, which, among other things, was given an award of 2018 Better Scientific Software Fellowship. With this, I'll just let you start with the presentation.
Thank you very much. Thank you very much for inviting me. And thank you, Alex and Tanu. Yeah, today I'm gonna talk about containerized workflows and how to make use of this emerging paradigm of container native workflows in the context of testing systems in general, but more particularly distributed systems, distributed storage systems. So before I get started, let me warn you that there are a lot of dogs around me. So you might hear some barking, so I apologize in advance. And then let me start with first telling you a little bit about me. I am from Mexico. I did my bachelor's in my hometown's university, which is the Universidad de Sonora it's the northwest of Mexico, which is the bordering state. Sonora is the bordering state with Arizona. After that, I spent 4 years as a research associate at HP Labs, working a lot with relational databases. Then I joined the PhD program at Santa Cruz, and in this time, I did a lot of internships. It took me a long time to finish my PhD studies, and so that gave me the opportunity to intern at different places, from startups to national labs. And currently, I'm a research scientist at UC Santa Cruz, working as a lab member of the Systems Research Lab, and I'm an incubator fellow at CROSS. CROSS is the Center for Research in Open Source Software, as Alex mentioned, and that this is a center that supports work from PhD students that are geared towards creating open source communities and finding sustainable models for these communities. And I'm also an adjunct professor, as Alex mentioned, at the University of Sonora. I also love mentoring. I've been mentoring for quite a bit now, and that's something I enjoy a lot. So, is this I forgot to ask? Is this a grad level class, or undergraduate level class, or both?
It's actually a cross-listed combination. It was initially a graduate level class, but it now has a cross-listed section for undergraduates as well.
Okay, cool. Yeah, if there are undergrads in the audience, I encourage you to take these opportunities over the summer to reach out to these communities, because it's a very great learning experience, and now we can do it virtually, so very nice. So yeah, let me start with the outline. As I mentioned, I'm going to talk a little bit about containers, just for the sake of completeness, start explaining what containers are, then talk a little bit about the container native paradigm and what workflows in general are, then combining containers, both containers and workflows, talk a little bit about Plopper, and then look at an example with how do we use container workflows using Ceph. And then I'm sorry, these is scheduled for an hour-ish, an hour and a half, or an hour?
No, this is an hour
Okay.
presentation slot.
Okay, cool. So I might not be able to reach to the end then, but I'll try to do my best. So let's start with containers. What is a container? Container is defined as OS level virtualization technology. It's usually introduced by means of comparing it to traditional hardware virtualization technology. If you're familiar with things like VMs in general, you know that there's a hypervisor, a hardware virtualization layer that you use to give the illusion to different operating systems that they're running on a machine on their own. And this has some disadvantages, some of them being that it has performance overheads. So people from industry, from the cloud computing world, specifically Google back in 2006, was doing virtualization in a different way by virtualizing the operating system. And what this means is that through some features of the Linux kernel, in particular namespaces and C groups, resource groups, gives the illusion to applications that they are running on a machine of their own, even though they're sharing that kernel with multiple applications. And this has the advantage of being lightweight. It's not as heavy as virtual machines, and it's also less in general is less resource intensive. So if you're familiar with Docker, Kubernetes, it's all about containers, and that's what people are increasingly using in the cloud computing world. The main benefit of using containers is that you bring your own environment, the entire stack, to shared infrastructure. So back in my day when I was an undergrad, like 20 years ago, we would set up a web service, and we would need to deal with installing a database, installing a mail app server, installing a web server, and it was a pain. Like right now, if you're familiar with Docker, you just run one command, you bring all that knowledge that someone already poured into a container image, and you run easily. So this notion of bringing your own environment, it's quite popular. It has a lot of implications, and things like data science in the data science world. This is picking up also quite significantly because it takes time to prepare environments in general. So what about workflows? Workflows, what is a workflow? Workflow, it's at the abstract level, is just a series of steps that it's an order of executing tasks. There are very different ways in which we can visualize workflows. There's, for example, this is a workflow that people use for using Git, like Git development workflows. This is a software delivery workflow that has humans in some steps, like for a software project, or orchestrating like a data science pipeline. But in general, it's a series of steps. And there are different workflow languages that we can make use of in general. Some of them are visual, like this one. This is an XML-based way of defining workflows. There's also like markup language based. In this particular case, this is a YAML file for CWL. CWL it's the common workflow language standard for defining workflows. And this is very popular in the biosciences world. People are making use of these to specify workflows of bioscience related pipelines. In a pipeline, I interchangeably use pipelining workflow throughout this talk. This is another example that it's more programming language specific. So there are syntax, there are different ways for defining workflows. In this case, I'm showing you a workflow in Airflow. Airflow is a framework for defining workflows, and this is Python based. So when you define a workflow, it actually looks like Python, and it is valid Python code. So there are in general different ways of defining these workflows, different languages and alternatives for specifying this. And there's also engines. So we have workflow, and we have workflow languages, and then we have engines. And on the engine side, it's very straightforward. We have an engine which is given a workflow specification, and this engine is in charge of running it for us. We're automating by defining workflows, and if they are like purely machine readable, then we are automating tasks. So these engines are in charge of allocating resources or running steps, keeping track of their statuses, monitoring resource utilization, logging, and general like generating provenance information, notifying and whatnot. And there is a lot of engines out there. This is just a very tiny example that of workflow engines that one finds in the wild. There are different ways when one say workflow engines, there are different ways of interpreting what workflow engine is, and it depends on many different domains. Like if you're like HTC Condor, it's defined as high throughput computing. If you're familiar with the LIGO experiment, a lot of that data was processed through this system, which is heavily used in the scientific world. Luigi is another example. It's an engine from Spotify. They use that internally to run their workflows, like data science workflows or anything that users want to orchestrate. They submit to the scheduler and they run it. Apache Airflow is the same, but from Airbnb initially, but now it's quite popular in different domains. And Daxter is kind of like the new kid on the block on this flavor of Python-based workflow engines. MLflow, it's very popular in data science world. MLflow is used in this emerging area of ML ops, which is marrying DevOps with machine learning and data science. In Argo, it's used in Kubernetes. It's a way of automating workflows on Kubernetes. And as I mentioned, there are like many. There's just too many to list. You're familiar with the awesome format of creating lists on GitHub. These are two lists that have like literally hundreds of tools of workflow engines. And then there's also this notion of platform, like a workflow platform, where you just not have the engine, but you also have a web interface / services around workflows that allow you to, for example, store data sets for example, if you're familiar with GitHub Actions, you can think of GitHub Actions as a workflow platform that it's listening to GitHub specific events and triggering workflows. And there's a lot of automation that people are bringing through their GitHub projects. The other day I found a guy, he was like automating his house with commits. Like he would push a commit to a GitHub repo, and then he would by using these IoT smart devices, he would do things like turning on and off lights and whatnot. Collecting knowledge is another example that it's more data science driven, but these platforms allow people to not only define and execute workflows, but also share and create context around these workflows. So that's in general like an overview of workflows, workflow tools, and workflow languages. Now let's look at what do we mean by containerized workflows. In this, when we look at the intersection of containers and workflows, we can see them from 3 points of view. There's the way we could taxonomize what's out there in terms of research and tools and technologies. One is existing engines that are bringing support for containers in the form of plugins or add-ons. There's also the container native approach, which are tools that are specifically written for containers, and the only thing they run is container native workflows. It's containerized workflows. And cloud native, which is a specialization of this world of container native. And I know it's a bit confusing, but this is a diagram that helps visualize it. So we have in general workflow tools, and like the ones that I showed you previously, we have workflow tools that where you can execute things even if you're not running containers. Like the tasks, the little nodes in your workflow, they run basically anything. And one of those things that they could run is containers, thanks to plugins, thanks to add-ons that you bring to the engine. And then we have the container native approach, which is you can only run workflows that are containerized, where tasks run on containers and only on containers. And then within this universe of container native, we have cloud native, and cloud native are those tools that not only assume containers, but they assume Kubernetes, a Kubernetes engine running and orchestrating this. So just for the sake of completeness, what do we mean? What it's the container native paradigm? If you're not familiar with this term, container native is basically just using containers for everything, not just what you would think is kind of like the meat of a workflow, which is maybe like running an application or deploying a service, but it's more than that. It's basically using containers for everything that we do, from building software, dealing with data, running tests, analyzing data, deploying models, like everything in the pipelines that we run uses containers. Or to put it another way, we follow the container native paradigm if we don't install software directly on our machines. Like if you don't ever run apt-get on your laptop, or brew install or whatnot, like these packages that are native for your operating system, if we don't run them, if we don't install this software directly on our hosts, and instead run this software in containers, then we follow in the container native paradigm. Like for example, in my laptop, it's you would say relatively in a pristine state, because I don't install anything. Like the only thing that I install is like the web browser, like the personal productivity tools, web browser, calendar, email application. That's it. And an editor and a terminal. Everything else, like if I want to run Jupyter, then I run Jupyter in a container. If I want to run, if I want to run curl, I run curl in a container. If anything, it's nice because it allows you to ensure that you don't have conflicting packages in your machine. Like even Node or all these tools for developing are in a container. And what a container native workflow looks like is, like I mentioned, something like this, right? For example, in this particular case, this is a study that one of our students run on. They work on with networking simulations. So you see here an experiment that is downloading some data from a web server. And as I mentioned, even something as simple as curl breaks, if depending on where you run it, because there are different versions of curl and they support different flags, and depending on what you're doing with curl, you need to ensure that you're running the exact version that you're expecting. And then for running experiment, in this particular case, this uses Contiki, which is a networking simulation platform, a framework. And then for processing results, then this is using Anaconda, the Python Anaconda distribution. So this is an example of containers. I mean, container native workflow. So that's in a nutshell. This we already covered containers, we covered workflows, and now we've been through the intersection of the two. And now I'm gonna give you a brief description of the tool that we developed in our lab and that we use to run experiments. And I hope I can get enough time to cover that use case for testing distributed systems using this tool in the container native paradigm. So this is, as I mentioned, a project supported by Cross. So we are working on incubating this project and creating a community around it and finding sustainable models for this project. So when we follow this container native paradigm and we start experimenting with it and trying to follow it, try to do everything in containers, there are some things that arise, practical problems that arise. One of them is that there is a lack of support for automating like multi-container workflows. If you use one container, then that's fine, but eventually we want to install more things and then more things and then more things, and then you end up defeating the purpose of containers by having everything in a single image. And for these, Docker or all these engines don't have built-in support for multi-container workflows. The other thing you find is that depending on where you want to run, you might not be able to use Docker. And then if you cannot use Docker, which is kind of like what runs on all personal computers, if you cannot run Docker, then you start looking at differences, suitable, like subtle differences that take a lot of time to deal with. For example, Singularity is a container engine that works in HPC contexts. So if you want to run containers in an HPC center, you cannot run Docker because it has some security issues that Singularity addresses. But then the way you interact with the Singularity container engine it's quite different from what you do with Docker. So then you are in this scenario where you use containers because you don't want to deal with portability problems, but then as soon as you move to another platform, then you don't have portable workflows anymore, or portable containers. And the same is true for other things like builders, and I'll describe what a builder is. And the third thing is there's this lack of common orchestration. If once we move to a shared infrastructure and we want to run our workflows, our containerized workflows there, depending on what's the resource manager that it's managing that pool of resources, you have differences in the way they use them. And it's a pain to deal with them as well. And by the way, feel free to interrupt at any point in time. I'll be happy to answer question. And so this is kind of like from the practical point of view, this is what we're trying to address, because this is things that we experience ourselves when we try to, we got very excited about this container native paradigm and all the things that you can do with all the things that containers solve. But then we faced this, and then we couldn't find anything that would help us with this. So that's why we built Popper. So when you containerize commands, right, you end up, let's say you're working on a project for homework or a small research project, and then you start containerizing your study. Then we start running these commands, right? And then we have the problem that even though we're using containers, there still are these different ways in which we run these containers. And that information is usually shared in a bash script or in a README file. But again, depending on where that runs, that might not work. And then we're back to this problem, not having portable workflows, which was the why we were using containers in the first place. So what we came up with was this very lightweight syntax for specifying these workflows that allow users to express what they would otherwise be typing manually in a terminal or in a bash script, but that allows us to abstract the details of where this is running. So this is an example of a YAML file that is in the syntax that we expect that runs. It's actually a bioinformatics pipeline. It's engineering. It's pulling some data, some sequences, files, building an image, running some analysis, and then validating the results. It's for in this domain of genomics. And one of the things that you notice is that it's very close to what you would type on, if you compare with the last slide, right? It's in this case, you're saying Docker run, what you run, and what do you pass as arguments, which is pretty much what you would do on the terminal. But we are now doing it in a structured way. And this has the advantages of solving this problem of having multiple flavors of containers in shared infrastructure. From the point of view of the user, as a user, this is what I want to do. This is the logic of my experiment and my analysis. I want to fetch data, run analysis, validate output. That's it. I don't really care where, and I'm using Docker containers, and that should be enough, or at least that's what we think. So when we have this multi-container workflow, and we go to share infrastructure, then we face all these different alternatives, and we don't want to deal with them. So what Popper allows us to do is to have this abstraction layer in between those things that allows us to do, okay, if I'm running locally on my machine, I do Popper run, and that works on Docker. But then let's say I am now logging into an HPC system, and that is running Singularity, for example. As I mentioned, the logic of my experiment doesn't change. I'm using containers. I have a container engine, and I should be able to run everything. So what we have, that's what we do, and when users run on different platforms, they can defer dealing with the particularities of these different engines to container engines to Popper. And that allows them to have portability on containers. This is in the case for container engines. The same applies for builders. If you're familiar with the container technology, you might know that when you build Docker containers, you need to be root. Nowadays, you can run Docker in a rootless way, but for building images, you need to be root. So there are different projects out there that are solving this issue by creating containers outside of an engine and creating containers in user space. And there are different ways of building. Again, the same story repeats. They solve the problem, but each of them need to be used in a very particular way. And from the point of view of the user, I have the Docker file. If you're not familiar with Docker files is the way you specify what your image contains. And it's a recipe for creating images. So from the point of view of users, I already have the recipe, and I don't really care how the image is being built. I just want to build it. I want to be able to build a Docker image and run it, or a container image and run it. So from the point of view of the user, if I do pop a run, then this is going to build images in whatever engine I'm using, or I can say, oh, I actually want to build using BuildKit. And then Popper deals with the peculiarities of building with BuildKit. The principle, or the main two things that allows us to have this layer of abstraction behind these different flavors of containers, the lowest common denominator is Docker files and standard open container images. So open container images, it's a standard for defining the images, and that came up from a group of companies that didn't want Docker, the company, to be the only ones dictating how Docker images would look like. So the OCI, the Open Container Initiative, was created, and that initiative is working on defining standards in the container world. In the case of images, container images, the OCI specifies a format, and that image format, it's supported by all of the tools out there. So from the point of view of for example, you can say to any of these container engines, you can say, run this image that is on Docker Hub, and they will pull that image from Docker Hub. And if they need to transform it internally to another format, they will do that. Or they can run directly. But they all support it. And the same way for building it. Like all these tools, when you build an image, they produce OCI compliant images. So that's the common lowest denominator in terms of the tools. And the same goes for Docker files currently. All these tools support Docker files, so you can build images from Docker files. And from the point of view of the users, that's what I deal with. I as a container technology user, I specify what my image is going to contain, and then I say how to run things using containers, which is what we're expressing in this file, in this workflow specification. And then we defer to Popper to do to deal with the details. The same applies for orchestrators. As I mentioned, different ways of orchestrating the same workflow. And as a user, I don't really care. I just want to run these series of steps, and I just want the platform to run it. So again, if we say Popper run, that works and assumes we're running on a host. But then we might be running on, let's say, a Slurm cluster, and one of our steps is an MPI step that is going to run in parallel, multiple machines. Again, Popper takes care of doing all that. Same for external tools that support containers, but for which we would need to rewrite this workflow. For example, Travis, if you're familiar with CI systems, many of these CI systems support running Docker. And if I want to run the same thing on, let's say, Travis, then I have to take this, translate it to Travis's internal definition, yeah, their own YAML syntax. With Popper, we say, okay, I want to export this workflow, export it to Travis, and then the tool does the work of generating that Travis file that it's going to allow me to continuously run my experiment on that platform. So this is in general our goal of having all these ecosystem out there that supports, that works with containers, and make it easier for users to leverage all those tools that are out there. Give me 1 second. So in terms of like abstraction layers, we see that we have the opportunity to raise the level of abstraction. So containers are now abstracting over multiple operating systems. So I have a container, and that container is going to run basically wherever I have a container engine that I can run. But then we have this issue that now we have all these different flavors, and now we don't have portability, even though that's the whole point of containers. So Popper is raising that level of abstraction and say, okay, over all these tools, I want to have, over containers, I want to have this single abstraction that works regardless of where I run. And one of the use cases for these is, as I mentioned, in, for example, a software project. Like it's very typical to go to GitHub, you have a project, and then the authors explain this in a README file in narrative form. This is how you try out things. And then we need to be copy pasting commands that's error prone. It's likely something's not going to work. Like think of when you're collaborating with other people, there's always something that works on their machine but doesn't work on our machine. Containers to some degree solve that, but as I explained, there are certain scenarios where that doesn't work. So what we are aiming for, it's to have this instead of, or in addition to having these descriptions, like what I'm showing right now, it's on the left. It's a paper that appeared in one of the journals in a conference. And then on the right, you have what it's called an artifact description that describes, it's in narrative form, a description of how you reproduce the experiments that are contained on that paper on the left. So this description, as you can see, it's in narrative with some commands there. It's basically a README that explains how to prepare a system, an environment, how to install software, how to run the experiment once you have everything you need. And as you can imagine, this always ends up not working. And the more complex your experiments are, the harder it is to reproduce. So what we are aiming for is, alongside these descriptions, or instead of, we can provide these workflows that are machine readable, that have all the logic, that if we used a container native workflow engine from the beginning for our own experiments, when we were developing this, and we were following this paradigm by making use of a container native engine, then at the end, we just share that. We put it on version control, share that along with our study, with our homework, with our project, our tests for a software project. And then it becomes easier for others to repeat and also to build on, to build more newer things on. To give you an example of how seamless this looks like in practice, this is a workflow for running for training a model. Now we know it's hot, machine learning, data science. Everybody wants to do this. So this is an example. You have a workflow that trains a model using a framework for doing distributed training. It's called Horobot. It's from Uber. And this is an example of what it would look like. We first download that data set, then we verify it, just checksum it and whatnot, and then run the training step. And when we're developing this, we might be trying out things locally on our machines, right? We say, okay, run this, I'm debugging things, I'm making it sure it works. But then eventually I want to scale it up, right? Because I might be testing with a small data set and just for debugging it. So, but when the time comes that we want to, let's say we have a machine that is managed by, let's say, Kubernetes, that we know has GPUs available, for example, then we can say, okay, I want to now use this Kubernetes cluster and say, I want to run the exact same workflow, but now running on Kubernetes. And then Popper is going to go look at the config file for that cluster, authenticate, launch tasks, and keep track of the execution of this workflow. But let's say that's not enough, because what I'm trying to do is actually quite resource intensive and time consuming. And I have access to Slurm. Slurm, if you're not familiar with, it's a resource manager that it's widely used in HPC systems. And this allows users to run computations in parallel. If the software that you're running knows how to use the proper libraries, in this particular case, this is MPI, then you can make use of that cluster of those nodes to parallelize your computation. And in this case, that's done by Horobot. That's what it does. So from the point of view of the users, we just add some details on how many nodes we want to use, which workers and whatnot. We might know that these are the workers that have GPUs. So we say, okay, we're going to use these machines. We can say now use 16 nodes or 32 nodes or 128 nodes. And we're using the Singularity engine because that's, as I mentioned, that's the one that it's friendly in HPC scenarios for dealing with authorization and security. And this just works. And as I mentioned, we didn't change anything. And now let's say I have what I have my results. Now everything is fast, but now I want to make sure that nothing breaks as, for example, new versions of Horobot come up or new libraries of NumPy or whatnot are released. So then I can continuously test this by exporting to Travis, and then I enable CI for my workflow. Let's say I run a very tiny experiment. It's not that time consuming. And I just schedule, for example, let's say I want to run every week or every month this workflow so that I ensure that nothing breaks, or that if something breaks, I know right away what broke. And for completeness, this is the picture of how long it takes locally, then when I run on a single machine, but in Kubernetes, on a GPU machine, and then on Slurm. There are many more examples. One that I wanted to talk, but before, one thing that I wanted to pitch to you and get your feedback on is this idea of a Popper cloud, where what we're starting to conceive is this scenario where you might be working locally with a workflow and everything might be going fine, but then eventually we reach usually it's due to resource constraints. We might not have enough CPU power. We might not have like GPUs in the scenario I described, or you might be experimenting with specialized hardware like storage, special storage devices or network cards or whatnot. So the idea is that because we already support Kubernetes, right, we might be able to spin up very quickly a Kubernetes cluster and have a service that others can log into. And if we have something like a single sign-on interface to it, then I could say, oh, everything works locally, but it takes too long. Then I want to log into my public cloud, download credentials, and now I would say, okay, now run on Kubernetes using this config file that I got from the public cloud, and everything would get transferred and be back to being happy. Or asynchronous schedule things and say, okay, I want to run this, but I don't want to wait for it. Come back later. So any feedback you might have, we would really appreciate it. Do you think it's a good idea or not? The last thing, do we still have time? I would also like to take your questions.
Hi, Ivo. Ivo, I think, yeah, it would be good to wrap up like in the next 5 minutes, I think, and then we can take questions.
Sure. Yeah. Yes, this is another short example of, this is the example I show you. It's relatively simple, right? It's a single machine. You scale it up, but then you take advantage of the tools out there. This particular case, when we're working with systems, we need to allocate resources, then build the systems that we're gonna want to test, and then look at results. This is very time consuming. It's very manual, and it's very error prone because there are so many steps, and any of them something can go wrong, or we might think that everything went fine, but something didn't go as we expected. So in our particular case, we have a system that is called SkyhookDM that runs on the Ceph storage system. And our workflow looks like this. So we spawn nodes on the platform, then deploy Kubernetes, then benchmark baseline the infrastructure, then run our experiments, and then plot results. And with containerized workflows, this can be made independent and automated. So when we do this manually, right? We, as I mentioned, we start doing looks like this, right? My work might not work depending on where we're running, and depending on the environment you're using. You might be using containers, but again, using containers, unfortunately, doesn't mean it's portable. So what we do instead is we pauperize all these manuals and instructions that we write. We also write, but that we create in the form of workflows. And then we are able to say deploy Kubernetes on a particular set of resources. Then baseline this, install Ceph, start monitoring, and so on. Yes, I mentioned there's a workflow for every high level step. And everything is documented, version control, it's self-contained. These repositories are self-contained in the sense that someone else does git clone, points to the right resources, hardware resources, and then everything works. We do a lot of monitoring because that's what we do. We want to check performance. This is how we check that our claims are true. But if we come up with a faster algorithm, then it should be shown in the monitoring and the graphs. if it's cheaper or faster, less latency, all these issues that we work with when we work with systems research. And we end up generating and analyzing a lot of our data through Jupyter. And I think that's it. That's all I had. I'll be happy to answer questions.
Yeah, let's open it up for questions.
Question for me. Near the beginning, you mentioned that you can categorize these tools as ones that support generic workflows versus container native versus cloud native. What advantages in general can I expect if let's say I'm running a cloud workflow? Why should I always use the cloud native ones, or or why use a more generic one?
Yeah, you can think of, so the problem with cloud native one, what that means, assuming Kubernetes, is that Kubernetes, you cannot always run Kubernetes, right? There are scenarios where that's not going to work. Like for example, even locally, right? Right now you can install Docker, and Docker has a Kubernetes cluster, but it's a single node Kubernetes cluster. And you might want to test things that for which you might not be able to or you have different flavors of Kubernetes that that you have to deal with. So there's, I don't know if you're familiar with OpenShift from Red Hat. So you have this issue of distributions of Kubernetes now emerging. And you have different ways of, it's kind of like a pattern, right? Even though Kubernetes should solve the problem of portability, because it's a system that is very complex and is trying to address so many use cases. It's not, you have this issue where you work with a system that runs Kubernetes and it should run what you want, but it's not, it cannot, because it has some particularities to it. Did that answer your question?
Yes, it did. And kind of related to, so the scenario where I should use the Kubernetes specific one is when I know that it fully supports my use case. Is that because it provides advantages in simplicity or something?
Yeah, well, the other thing is there's also, like if you look at the workflow engines that run on Kubernetes, they have their own specific syntax. Even though if you assume that you're Kubernetes only, you still have this issue of multiple languages, multiple specific there are specific things that you need to be careful with if you're running on a particular workflow engine. Like you cannot port workflows from, for example, Argo to Pachyderm, which is another workflow engine. And yes.
Sorry, we have a question from Michael also over here.
Yes.
I didn't want to interrupt you, but just
no worries. Sure.
That'll be quick. I'll try to be fair, even though I think that my friends who went to work for Docker and are part of a cult. But yeah, goodness, they only talk about that. I just want to address that one thing you mentioned about reproducibility of experiments.
Mm-hmm.
And you said that the problem is that most of it is written in human language. And I don't think it's the main problem, in that if these people were trained computer scientists, they would know how to use a configure, they would know how to use Meson or any kind of building tool that would actually be a big step forward. So how do you expect these people to use something as complicated as containers when they're not even trained to use a bash script?
Oh, yes, I agree. I mean, this assumes that that you know how to use containers, right? That you know how to use a bash, that you know what a bash script is, that you know how containers work. That's a prerequisite. But we're heading there, though. Like, I know people that are not computer scientists. They're like geophysicists or computational biologists. Like, there's this foundation. It's called the Carpentries. And if you look at the people that go to those workshops, that's the next generation of scientists. And they all know how to use the terminal and how to use a text editor and write Python scripts. And I think that's the crowd we're targeting.
Okay, thank you.
Yeah.
Ben, did you have a question over here?
Yeah, I saw that you had Slurm. If you looked at other resource managers like PBS Pro.
Mm-hmm. So right now we don't support other than Slurm and Kubernetes, but the architecture of the tool it's extensible. So we have plugins basically, and yeah, we would love to have those. We don't have enough. Actually, we haven't got a request for those yet, but what we welcome pull requests always.
Okay. So I have a related topic in terms of workflow, and I think Tanu and I had this conversation 2 years ago. 2 years ago or so. Have you looked at trying to get the ECP funding, because this is something they're trying to do at the access scale?
Yeah, so actually yesterday, so this week is the supercomputing conference week,
Yep.
which is virtual this year. And yesterday we presented at the high performance container workshop. There's a workshop now for using containers in HPC, and they are definitely looking at this. From the exascale computing project, there is a working group that they're basically using Singularity right now. But there are other engines like Charlie Cloud. There's another one, I forgot the name. It's a new one from folks in Germany. There's new engines from NVIDIA that allows you to run container workflows in parallel. There's a lot of interest for sure.
Right, Ben. So even SciUnit is funded. I think I saw your question on one of the on the Research Colloquium discussion board that, yeah, so even SciUnit is funded through ECP, one of the ECP fellowships. And yeah, there's a lot of container interest within ECP, and all these technologies are applicable to them, but exactly what's the use cases is still pending. Yeah.
Yes.
Other questions? Ivo, I'll have several questions, but I want to watch the entire thing. I haven't been able to. So I'll send you questions separately over.
Sure.
Yeah.
Sure, no worries.
So I have a sort of administrative question of the examples you were showing. I noticed that in the script, there is this note that says 0 vulnerabilities found. Is this the container vulnerability, the script that generates data vulnerability, or who's detecting it and what?
That's the script.
That's
like so far we don't do anything other than launching things and waiting for them to end. One of the things we are planning on is adding logging, like and tracing, because some of these tools allow you to enable those, and then again have this abstraction and say, hey, if the engine supports it, can you please turn these on? And then capturing, for example, logs, or something that is very important for reproducibility is getting a snapshot of what the infrastructure looked like at the time that the workflow ran. Like what hardware was it? What operating system was? Like all that information that is important for when someone reruns it and something doesn't work. That
so
you
essentially
are able
metadata.
to exactly. Yes.
Interesting. Because I'd be very curious to know, probably ask Tano as well offline, whether if you rerun something and it generates the same results, do the logs have to be the same, or is there some function for that?
Yeah. There's a lot of interesting work there. There's a lot of work in provenance and in general from the software engineering community, like how do you automatically detect regressions in a more semantic way rather than just checking like raw strings, right?
Thank you.
Or the other is true, right? If let's say there are differences, does that actually mean that it's not the same? Yeah, a lot of interesting work in that area and problems.